Hello, everybody. In the previous lectures, we have discussed the wave function, the Schrödinger's equation, time-dependent, time-independent versions for a single particle. But what if we have more than one particle, two particles, three particles? It turns out that the particles at the most fundamental level cannot be labeled. You cannot say that this is electron number 1, this is electron number 2, this is electron number 3. This property is called indistinguishability. Quantum particles are indistinguishable. So I will talk about indistinguishability of quantum particles. This situation is something somewhat similar to a macroscopic case when you have two glasses filled with water. You mix water from the two glasses, and then you cannot tell which particular glass this water droplet came from. If the wave functions of two electrons, let's say, overlap, it is like mixing water. It is like mixing two electrons. You cannot tell which electron's position is measured, the first one or the second one. This is what we mean by indistinguishability. Indistinguishability has a profound effect on the wave function. It turns out that the wave function can be either symmetric or anti-symmetric with respect to an interchange of the coordinates of the particles. And this depends on the particle spin. The result is called spin statistics theorem, discovered by Pauli, Wolfgang Pauli. Spin statistics theorem has a consequence called Pauli exclusion principle. It turns out that you cannot have more than one electron per quantum state. And this, together with Schrödinger's equation, can be combined, this principle together with the Schrödinger's equation can be combined to explain pretty much all of chemistry, including the periodic table and including the types of chemical bonding, why atoms interact, bond in a specific way. All right, so without further ado, let us begin with this fundamentally important concept, idea in quantum mechanics, the idea of indistinguishability of identical particles. Suppose we have just two particles, let's say two electrons for the sake of definiteness. And these two particles are described by a combined two-particle wave function, which we denote as psi. It depends now on not on one, but on two coordinates, r1, r2, and time t. But the wave function itself cannot be measured. What you can measure is the probability density modulus psi squared, which in the two-particle case tells us, gives us the likelihood of finding a particle near a point r1 and another particle near the point r2. I am not saying particle 1 at the point r1 and particle 2 at the point r2, because particles are indistinguishable. Now, of course, you can distinguish electrons from protons by their mass, for example, or by the sign of their charge, but you cannot distinguish one electron from another or one proton from another. This is what is meant by indistinguishability. So, if you measure the probability density of finding one particle at R1 and the other particle at R2, there is absolutely no way of telling which particle is which. This means that if we exchange the arguments of the wave function R1 and R2, we should obtain another wave function which is physically indistinguishable from the original wave function psi of R1, R2. So the wave function psi of R1, R2 is physically indistinguishable from the wave function psi of R2, R1. Now, the two wave functions are indistinguishable if they differ by a constant number whose modulus squared is 1, because it is only the modulus squared of the wave function which is measurable. So we conclude that modulus squared of psi of R1, R2 is the same as modulus squared of psi of R2, R1. This condition is satisfied if the two wave functions differ by a number whose modulus squared is 1. So let's call this number C. In general, you can express C as exponential to the power I phi, where phi is a real number because exponential to the power I phi has modulus squared 1. Now, let us apply this interchange twice. Every time we interchange the coordinates, we swap the coordinates, the wave function gets multiplied by this number C. Let's interchange the coordinates twice. If we do it twice, then the first interchange multiplies the wave function by C. The second interchange multiplies by the wave function by C again, and it recovers the same wave function as we had before. So from this, it follows that C squared must have the value 1. In other words, this number C can be either plus 1 or minus 1. It cannot be exponential to the power, for example, I pi over 3 or something. Either plus 1 or minus 1. And if this number C has the value plus 1, that is, the wave function does not change sign if you interchange the coordinates, then such a wave function is called symmetric under exchange of coordinates. And if this number C has the value -1, the wave function is called antisymmetric with respect to interchange of coordinates. Now the natural next question is which particles have symmetric wave functions and which particles have antisymmetric wave functions. This is answered by the spin statistics theorem, which I would say it is one of the deepest results in quantum field theory. It was proven by the Swiss physicist Wolfgang Pauli in 1940, even though he formulated the spin statistics theory without proof a little bit earlier. I am not sure when, 1930th, give or take a few years. So this is what the theorem says. You already know that there are two types of particles according to their spin. Spin is that internal degree of freedom that can be kind of related to some sort of a, very loosely speaking, rotational motion of a particle around its axis, even though there are no truly point particles. Like an electron is really cannot be thought of as a little ball that flies around, but rather it is more of a cloud, which is distributed according to the modulus squared of the wave function. So nevertheless, all particles have internal angular momentum, which we call spin. And spin is quantized in the units of reduced Planck's constant, and it can assume the values which are either integer multiples of the reduced Planck's constant h bar, or half integer multiples like h bar over 2 or 3h bar over 2. And particles whose spin is integer are called are particles which carry interactions. For example, photons, gluons, postron interaction, and W and Z bosons, and gravitons if they exist, and Higgs bosons, and so forth. And particles with half integer spin are the particles that form matter, such as electrons, protons, neutrons, but also quarks, tau mesons, muons, and so forth. Now, the spin statistics theorem, that was a reminder, memory refresher. The spin statistics theorem says that all bosons have symmetric wave function. All fermions, particles with half integer spins, always have antisymmetric wave functions. And this symmetry is not something that can change dynamically as the system evolves. A symmetric wave function will always remain symmetric now and forever, and it always was symmetric. And antisymmetric wave functions will always remain antisymmetric. This is a fundamental structural property, rule, law of nature. All right. Okay, I will not even attempt to prove the spin statistics theorem. It is hard, complicated. There are some hand-waving arguments why the spin statistics theorem must hold, but I will not reproduce them as well because they are not very relevant to our course. But the formulation of the spin statistics theorem, and I hope that you hardwire this formulation into your brain. So I will repeat it again. Particles with half integer spin have antisymmetric wave functions, and particles with integer spin have symmetric wave functions. And by the way, the symmetric wave function particles with half integer spins are called fermions. The antisymmetric wave functions with half integer spin are called fermions, and the symmetric particles with integer spins are called bosons. So electrons are fermions, photons are bosons. All right, now, once we know that fermions must have antisymmetric wave functions, the Pauli exclusion principle follows almost immediately. Although I believe that Pauli exclusion principle was formulated in 1925 as a way of describing electrons and trying to understand the orbital fillings in atoms. And then Pauli generalized, he realized that his exclusion principle follows from a more fundamental statement, which is the spin statistics theorem. Anyway, consider two non-interacting fermions like electrons, and each of those fermions can occupy some stationary state, which we can label with with a set of quantum numbers alpha or beta, psi alpha of r, psi beta of r. Those stationary states solve some time-independent Schrödinger's equation. And now we imagine that these two fermions do not interact. Okay. Now we would like to construct a two-particle wave function which is antisymmetric with respect to an interchange of the particle coordinates. The first thing to try is, of course, to multiply. Let's say one fermion is in the quantum state alpha, the other one in the quantum state beta, and let's introduce the coordinates R1 and R2 to label the coordinates of those fermions. So psi alpha of R1 is the probability modulo squared of psi alpha of R1 is the probability density to find a particle at the position near a position R1. And likewise, psi beta of R2 is the probability density to find another particle at the position R2. So the first thing to construct this two-particle wave function is just to multiply the single particle wave functions together. So you will get psi alpha of R1 times psi beta of R2. Does this wave function solve time-independent Schrödinger's equation? Yes, it does. Yes, it does. Is it consistent with the spin statistics theorem? No, it is not. Because if you interchange the arguments R1 and R2, this two-particle wave function will not change sign. You will merely get psi alpha over 2 times psi beta over 1, which is not negative of psi alpha over 1, psi beta over 2. So we need to think a little bit harder, but not much harder. The only way to produce a two-particle wave function that does change sign if you interchange the coordinates is this anti-symmetrized product, psi alpha over 1, psi beta over 2 minus psi alpha over 2, psi beta over 1. So now if you interchange R1 and R2, this difference changes sign. And this factor of this factor 1 over square root of 2 is therefore proper normalization of the two-particle wave function to 1. Now imagine that both particles occupy the same state alpha. That is, you set beta to alpha. You replace the index beta, quantum state beta, with the index alpha. Then the two terms in the brackets in this antisymmetric combination become identical and they cancel each other. So the wave function collapses to 0. Now, if a wave function is identically 0, then this is no physical state at all. Therefore, and now the Pauli exclusion principle, two fermions cannot occupy the same quantum state. And so, like I said, Pauli exclusion principle was discovered by Pauli before the spin statistics theorem, but historically, but so we have seen how the slide shows how it follows from the spin statistics theorem. And the reason Pauli exclusion principle is the reason why atoms have the structure they have. Here is the periodic table of elements. So hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, and so forth, oxygen, and so forth. And now we will try and explain the periodic table of elements. So to understand the periodic table, we will treat electrons in atoms as approximately non-interacting. Now, of course, this is not exactly true. Electrons do interact because they're both charged. Coulomb forces cannot be switched off. But because they tend to avoid each other, like charges tend to avoid each other, each electron in an atom interacts with the nucleus, so to speak, more than it interacts with other electrons. All right, so in atoms, electrons occupy hydrogen-like shells, which are labeled conventionally. They are labeled with Latin letters K, L, M, N, which correspond to the principal quantum numbers n equal 1, 2, 3, 4, and so forth. Okay, so yeah, just a reminder: the energy state, the quantum states of an electron and a hydrogen atom depend on 3 quantum numbers plus spin. Those 3 quantum numbers are the principal quantum number n, which determine the energy of the state, negative Rydberg's constant divided by n squared. Then you have orbital quantum number L that gives you the magnitude of the orbital angular momentum, h bar square root of L times L plus 1. Then you have, and the orbital quantum number can assume the values from 0 to n minus 1, principal quantum number minus 1. The magnetic quantum number gives you the projection of the orbital angular momentum on a particular axis. M, magnetic quantum number, can assume the values from negative L to positive L. So negative L plus 1, negative L plus 2, all the way up to L. And finally, we have spin quantum number, which determines the projection of the spin angular momentum on a particular axis. And the spin quantum number for electrons can be either negative or positive 1/2. All right, so the principal quantum numbers assumes the values 1, 2, 3, 4, and these values correspond to the shells, which are labeled as K shell, n equals 1, L shell for n equals 2, M, N for n equals 3 and 4 respectively. And for a given n, principal quantum number, the shell contains n squared orbitals. Because n squared is the number of combinations of the orbital quantum number L and the magnetic quantum number m, so n squared orbitals. And each of these orbitals can be occupied by at most 2 electrons with spin up and spin down. Why at most 2? Why not 3? Well, because of the Pauli exclusion principle. Spin up or spin down are also labels of the quantum state, and you cannot have more than 2 fermions per quantum state. And electrons are fermions. So those orbitals, I have actually an extra slide about this nomenclature. So those orbitals are labeled also with lowercase Latin letters. So when the orbital quantum number is 0, then the orbital is labeled with the letter S. When L equals 1 orbital, it is a p orbital. When L equals 2, it is a d orbital. When L equals 3, it's an f orbital. When L equals 4, it's a g orbital. Now, in principle, you can have L equals 5, 6, 7, and so forth with the letters H, I, and J is skipped. K, L, M, and so forth. But in practice, in real atoms, the values of the orbital quantum number bigger than 4 do not occur. They do not happen. Now, each orbital can hold spin and available states per shell in the n already hints at the periodic structure of the element. So let's return to our periodic table. So excuse me. Electrons fill these shells in the order that minimizes the total energy of the atom. So starting with the lightest element, hydrogen, we have 1 electron, which is in the shell with n equals 1. So this is the, sorry, this is the K shell. This is the K shell. This electron is in the state S equals S, so L equals 0 and M equals 0. Then we add another electron, we increase the number of protons in the nucleus, and so we go to helium, and we add an extra electron to keep the atom electrically neutral. So now we have 2 electrons, both of which will be in the s orbital of the K shell, and their spins are opposite. Spin up and spin down. Helium is an inert gas, the first inert gas atom in the periodic table. That is, inert means that it doesn't chemically interact with anything. Then we increase the number of protons in the nucleus and the number of electrons, and we arrive at lithium. Lithium has the K shell completely filled, and you have an extra electron in the L shell, capital L, yeah, n equals 2. That extra electron is in the 2s state, so second shell s orbital, 2s state. Then you add another electron to the 2s shell, and you have beryllium and so forth. You fill all this, increase the number of protons in the nucleus, you increase the number of electrons by 1, and you, in this way, you build up this periodic table all the way to argon, which is number 18. Now, so this works nicely for lighter elements up to Z equals 18. So the shell fills the intuitive order, first 1s, then 2s, then 2p, then 3s, then 3p. But for heavier atoms, after argon, electron interaction starts to play a role, and in particular, the screening of the nuclear charge by the inner electrons, by the inner shells, they modify the energy ordering of the orbitals. So as a result, the 4s orbital in potassium becomes lower in energy than the 3D orbital. And electrons begin to fill the next shell before the previous one is completely filled. So you see in potassium, you have the argon has 8 electrons in the outer M shell, and in potassium you have the instead of 18, right? In argon, the outer shell has 8 electrons instead of the 18 electrons which are allowed. But in potassium, sorry, yes, and in potassium, the next shell is not the M shell, but the N shell. So the extra electron goes into the N shell. All right, and so this change in the filling is due to the interaction between the electrons. So this our picture based on the non-interacting electrons breaks down. So these chemical properties, the chemical properties of the atoms are determined by the outermost shell, which is partially filled. And this is why the elements in the same column of the periodic table have the same chemical properties, because they have the same valence band, valence shell structure, because the shell which is partially filled is called the valence shell. All right. Now, all right, so next let us discuss the reason why atoms bond with each other the way they do, chemical bonding. Atoms bond when bonding lowers their total energy of their electrons. So if the energy of the electrons of two atoms when they are far away from each other is higher than when the two atoms are bonded together, then the atoms will bond together. There are 4 main mechanisms of bonding, which are the van der Waals bonding, the ionic bonding, covalent bonding, and metallic bonding. Van der Waals bonding is the weakest. It arises when the dipole moments of two atoms. So the dipole moments of an atom is a proton, is a positive nucleus, and a negative electrons orbiting or somehow distributed around the nucleus. And in general, the dipole moment of an atom is 0 on average. But atoms do not exist in vacuum. Atoms interact with external electric fields, which fluctuates, randomly changes in time, and also electrons in atoms undergo what is called the quantum fluctuations. So the dipole moment of an atom is 0 on average, but it is not 0 at every moment of time. It fluctuates, it randomly changes around the value 0. Now, suppose the dipole moment in one atom has a non-zero value at a particular moment of time, it creates an electric field around this atom, a weak, small electric field. But that electric field polarizes another atom somewhere in the vicinity of the first atom. So the second atom also becomes polarized. And now we have 2 dipole moments. And this effect, this polarization effect results in an interaction now between 2 atoms. And this interaction turns out to be always attractive. This weak attraction, the energy of this weak attraction decreases as the sixth power of the distance between the two atoms. And this interaction is called van der Waals interaction. Even the noble gases, helium or argon, experience van der Waals interaction. And this is the reason why they can become liquid or even solid at low temperatures and at high pressures and low temperatures. Now, the next interaction type is the ionic bonding. Ionic bonding happens between elements, well, metals of groups 1 and 2, and non-metals of groups 16 and 17. So elements which are in the initial two columns of the periodic table and elements which are in the last and one before last columns of the periodic table. When two such atoms approach each other, electrons transfer becomes energetically favorable because the metals from group 1 or 2 are happy to lose electrons, and the non-metals from group 16 or 17 are happy to gain those electrons so as to have the outer shell corresponding to that of a noble gas. Once this transfer occurs, the resulting ions become one positive and one negative, and they are strongly attracted to each other. And this is ionic bonding. So this bonding is driven by electrostatic interaction, electrostatic attraction due to electron transfer from metals to non-metals. Examples include table salt, lithium oxide, and so forth. Next, if electron transfer is not favorable, for example, you have two atoms of the same kind, two hydrogen atoms. Like, why would one hydrogen transfer its electron to another hydrogen? Still, atoms can share their electrons, and this is called covalent bonding. So most atoms strive to achieve the same valence shell configuration as that of noble gases, because this configuration is energetically most stable. So, for example, if you have two hydrogen atoms, so a single atom has one electron in its lowest K shell, but the noble gas configuration, that of helium, has two electrons. So now if you have two hydrogens brought together, they share their electrons, and now each hydrogen has a stable helium-like configuration of its K shell. For light atoms, this leads to what is called the octet rule. So atoms tend to form bonds so as to have 8 electrons in their valence shells. Here are some examples, like hydrogen, molecular hydrogen, water, carbon, and they mean carbon as in diamond. Silicon, again, diamond. Carbon, diamond, and silicon, crystalline silicon, have diamond structure, of which I will tell you in the next lecture, I think. All right, so covalent bonding is directional because it depends on the overlap of specific orbitals. And this directionality is responsible for huge variety of molecular structures and crystalline structures of covalent crystals, such as diamond, silicon, silicon dioxide, gallium arsenide, and so forth. And finally, metallic bonding. So metallic bonding is similar to, in spirit at least, to covalent bonding, but on a much larger scale. So a metal crystal is one huge macroscopic covalent molecule. So instead of electrons being shared between two atoms, they are shared by a huge number of atoms in the crystal. The valence electrons in a metal are delocalized. They form an electron gas, if you will, which permeates the entire lattice, the entire metal. And the positively charged ions, they sit in the nodes of the crystalline lattice, held together by this sea of valence electrons. The valence electrons, the electrons in a metal, are free to move, which gives the metals their characteristic properties, such as high electric conductivity, high thermal conductivity, elasticity, high optical reflectivity, and so forth. So, to conclude this lecture, when Dmitry Mendeleev arranged the elements into a periodic table in the 1860s, he used atomic mass. He noticed that the chemical properties of elements vary periodically with the mass of the elements, or molar mass of the elements. He didn't use the term atomic mass because he was not 100% sure that atoms existed. And the idea of nuclear charge had not been discovered yet. But by a fortunate coincidence, atomic mass and atomic and nuclear charge, they are approximately proportional to each other, at least for the lighter elements. So the true periodicity, the periodicity in the atomic number, which reflects the number of protons in a nucleus, is reproduced correctly if you follow the atomic mass. For about 70 or 80 years, the reason behind the periodic table of elements was not at all clear, so it remained a mystery, and people had to treat the periodic table like as a fact of life. But they didn't. It worked. It was empirically true, but it didn't have a theoretical justification. And quantum mechanics finally uncovered the structure beneath the periodic table. It explained not only the periodic table, but the entire architecture of chemistry, which is one of the most spectacular triumphs of quantum mechanics. One of many triumphs of quantum mechanics. So with this, I would like to conclude this lecture, and thank you all for your kind attention.